Alright, these are the solutions to our second exam, and I'm going to just do some typing, click back and forth with StatCrunch, and hopefully this will be helpful. So this first one here, we're going to create a scatter plot predicting the percent college ready from the low income percent. Alright, let me skip over here, Illinois school data, so we'll do a graph, scatter plot. We want to predict the percent college ready from the low income percent. So the percent college ready is the Y. And then we need a label. The x-axis and y-axis will be fine. And do a title, something like this. So college readiness versus the low income percent. Hit compute. There we go. A nice little graph. Options, copy, copy image, and then do our paste special. There we go. All right, so looking at that, let's see, definitely a linear relationship. And notice here I said a little differently, explain clearly using language that a reporter might use in an article. So that's just saying as the percent of students who are low income in a school increases, the college readiness rate decreases. Right? So more low income students just means less who end up college ready. Alright, so let's compute the linear correlation coefficient and round to 2 decimal places. So let's do, you know what, I think we're going to need a residual plot. So I'm going to do stat regression, simple linear. We're going to do low income percent, predicting college readiness. And let's see, we want a graph, we want a residual versus x values. Oh, and I think there was a predicted we want in there too, right? Westinghouse High School in Chicago, 83.1% of its students qualify as low income. Calculate the residual. So we have the actual, 53.5% are college ready. So we need to get the predicted Y. So we said 83.1. All right, so let's hit compute. All right, so the first question was the correlation. So R is about negative 0.78. That was up here. R is approximately negative 0.78. The equation for the least squares regression line, round to 4 decimal places. I'm going to copy this and then I will edit it when I get in there. Let's see. I guess I didn't really need 4. That's way too much. We could have rounded to more than that, or less than that. That's fine. All right, so we're going to predict the residual. Or we're going to calculate the residual. First of all, the residual is the observed value minus the predicted value. And in this case, the observed is 53.5%. And our predicted 17.9. Whoa. And so, what is 53.5 minus 17.9? I did not have a calculator handy. Let me do that. Desmos. Oh, it's not that one. It is not graphing, but scientific. That's the one. All right. So 35.6 is the residual. And then we're going to determine if Westinghouse is performing as expected, better, or worse. So definitely better. Westinghouse is performing much better than expected. Their residual is 35.6, very positive. So this means they had 35.6% higher, percentage points higher than what they would predicted based on their low income percent. I wonder if we can find them quickly in here. This is maybe a bad idea, but there's the graph. I bet Westinghouse is, they got to be over here somewhere, right? This one, 83.1, that one maybe? Nope. This one? Nope. All right, let's try find Westinghouse. And there they are, right? So they're one of these outliers. The line is down here, and they are way above. All right, residual plot. We did make that. That's over here. There's our residual plot. Let's clear Westinghouse out of there. All right, options, copy image, and then paste special device independent bitmap. Let me go to a new page for that. Okay, and then we are supposed to use it to explain whether or not a linear model is appropriate to consider in this case. So yes, there is no pattern. The spread is pretty consistent. And there are no influential observations. Now, it actually isn't clear. This one might be influential down here. Let's maybe go find it. I didn't need you to do this because there's all these points here. We basically talked about this in class, but let's go to that row and then just take out the low income percent, 3.4. And then run this regression again, low income percent and percent college ready. And let me go back here and let's look at differences here. Right, the slope or the y-intercept is 68.1, 67.8, negative 0.6, negative 0.61. Correlation negative 0.79, negative 0.78. Right, see, so it really didn't change anything, even though it is a pretty significant outlier down there. It didn't actually affect it too badly. So we could say yes, a linear model is appropriate. All right, moving on to the next one. We're going to create a password. We have to have 4 characters. They can be letters, all lowercase, and numbers, and the characters must all differ. So if we think of the first character, it could be any of the letters, 26 letters, any of the numbers, 0 through 9, that's 10. So it could be any 36. And then there are only 35 choices for the second one because they have to all be different, and 34 and 33. You could also think of that as 36p4 if you wanted to. That is fine as well. It's a permutation. You're taking 36 objects, you want to choose 4, and order matters. So this number... Alright, so what is that? 1.4 million? That's a lot of passwords. Even just with 4 characters and 4 letters. Alright, suppose that you are a volleyball team organizer. There are 10 teams signed up, and you think it's a good idea to have each team play every other team. How many games are possible if each team plays every other team once? So the best way to consider this one is to look at each game. Really, how many possible games are there, right? And so for a game, you have to pick 2 teams. And you just need 2 teams. You don't care which team is first, which team is second. You're just going to randomly choose 2 teams. And so and those 2 teams have to be different. They can't be repeated. But the order of those teams doesn't matter. So that's a combination. This is just 10C2. And that's actually pretty easy to calculate. But we can go over here. There it is. NCR 10, 2, which is 45. All right, Hamilton. All right, we have 46 tracks. I really enjoy about 20 of them. This is a true story. This is not actually true. I wrote this a while ago, so I did not do it in your exam, but I kind of stole this question. Suppose I listen to 10 songs. What's the probability that of those 10 I don't like any of them? So the probability that we like none of them. Well, that would be, if we think of a fraction here, I'm going to do an equation. So it's the number of ways to like none over the number of ways to pick any 10, right? It's a probability. What's the probability that we won't like any of them? And so that numerator, how many ways can we like none of them? Well, from the 26 songs that we don't like, I want to choose 10 of them. I don't care about the order. I want to just pick 10. And then the probability of getting any 10 would be from the whole 46 in the album, I want to choose 10. All right, so let's do that. Let's do NCR 2610. I want to like 10, and then divide by NCR 4610. So that's about 0.0013. So that's pretty unlikely that if I play 10 songs that I won't like any of them. I mean, I like 20 out of the 46. I'm bound to get a couple that I like, right? So that'd be pretty unusual if that happened. All right, basketball. Players are sometimes given the ability to shoot a free throw for those who haven't watched a lot of basketball. Sometimes you get in a rhythm and you start making them, like if you keep getting fouled. Sometimes you go long stretches without missing. Other times, like maybe the end of a game, you're really nervous. That might cause you to miss. So you might have an overall percentage of made free throws, but it might not be consistent. It might vary based on the game situation. So Steph here, last year he made about 87% of his free throws. Suppose we track him over the course of a few games until he shoots 20 free throws total. If we let x be the number of free throws, does x follow the binomial distribution? So first of all, are there a fixed number of trials? All right, well, there's not a fixed number of games, but we're not counting games, we're counting free throws. Yes, that's 20 free throws. By the way, you do need to state, like, explain why they're met in this context. So 20 free throws. Second, two outcomes, right? Two outcomes. Yes, it's a make or miss, right? Either you make it or you miss it. Are the trials independent? Well, in this case, are they independent? We just said above that you might get nervous. Maybe you make a bunch in a row, so that makes you more confident, so you're more likely to make the next one. And so in this case, no, because notice above, it might vary based on the game situation. And similarly to that, there's the constant probability. That's also a no, see number 3, same reasoning. So no, it does not. So it has to be all or nothing here, right? Well, what is happening on with my formatting? So no, this does not fit the binomial distribution. It has to be all 4 or it doesn't work. All right, number 6. Suppose an electronics company offers a $50 2-year warranty on a TV that costs $800. 95% of the time, it lasts a full 2 years, no repairs are needed. 4%, something minor breaks, costing about $200 to repair. And the remaining 1% of the time, there's a critical failure and it needs to be replaced. We're going to find and interpret the expected value of the repair cost. So actually here, the warranty price is kind of just in there as a distractor. So I don't really want to insert, I don't know if I can insert it. Can I insert a table without messing all this up? No, not really. All right, so let me do this. I'm just going to do an x and then a probability of x. So our possibilities are repair cost. We could have $0, right? And that would be 95% of the time. We could have $200, and that would be 4% of the time. Or we could have to replace it, so our repair cost is really a new TV, and that's 1% of the time. So the expected repair cost would be 0 times 0.95 plus 200 times 0.04 plus 800 times 0.01. And I think that should be $16, but it's been a long day, and I'm feeling a little lacking in confidence here, so I'm just going to go use my calculator. 16. All right. Trust yourself. Okay, so what does that mean? This means, on average, this type of TV have repairs that cost $16 over the 2 years. So it's not that you can expect to cost $16 or that it will cost $16. It can't. Either it's 0 or 200 or 800. But over the long run, this will be the average repair cost. The key there is that average. That's the key. All right, let's do a page break. Number 7, we have kidney cancer patients. Use the binomial distribution to find the probability that exactly 16 out of 40 will survive at least 5 years if the probability is the same as the current treatment, 0.2. So the survival rate is currently 20%, so the probability of surviving is 0.2. All right, so we need to use the binomial calculator. Sorry here, and I'll just open this one up, stat calculator's binomial. We have 40 Probability of success is 0.2. We want to find the probability of being exactly 16. 0.0019. Maybe we can, let's do this image in here. Yeah. There we go. The probability of at least 16 out of 40. What's the probability that at least 16 out of 40 will survive? Oops. What am I doing? I just want to make this greater than or equal to. So let's do the same thing. Copy image. Shrink that down. All right. So now the question is, would it be unusual for at least 16 out of 40 to survive at least 5 years using the current treatment? Yes, it would, because that probability is less than 0.05. Right? The likelihood of getting right now the 5-year survival rate is 20%. Out of 40 you'd expect 8, right? So the likelihood of getting 16 or more, the probability of getting 16 or more is less than 1%. It's like less than 0.3%. So that's very unusual. So it's definitely, that would be unusual if that were to happen with the current treatment. All right, next question. Suppose a fair 6-sided die is rolled 100 times and the number of times a 6 is rolled is counted. Determine whether it be unusual. So again, we need to find a probability compared to 0.05. To roll a 6 more than 20 times out of the 100. Well, this is a binomial. 100 rolls, that's n is 100. And we want to find, and p would be probability of success, which is a 6, would be 1 out of 6. And we want to find the probability that x, the number of 6s, is greater than 20. And so that'll be binomial again. We have n, and we're doing 100 rolls. Probability is 1/6. We want to find the probability of it getting more than 26s. All right, so let me put this down here. Well, let me paste it here, and then I'll just say the answer. 0.1519. All right, I should say approximately, but that's okay. Okay, next, using the school discipline data. Copy and paste your tables into your Word document. All right, so create a contingency table. Discipline data, contingency table of race or ethnicity versus SES, socioeconomic status. Table contingency with data. SES, socioeconomic status, race or ethnicity. I'm going to take off this test, don't care, and compute. And I find I need to get more than just the table. It's just going to let me paste that in there. Look at that, beautiful. Well, the font is not right, but that's okay. All right, so there's my contingency table. And we're going to create a conditional relative frequency just by asking. Right, so this is the conditional relative frequency distribution of socioeconomic status. So we want to know, how are these two socioeconomic statuses distributed? You know, what percent are free or reduced and what percent are paid? We want that broken down by race or ethnicity. So I think we want the column percent here, the column percent. So let's do options, edit, column percent. Let's double check. So is this telling us the distribution? So for students who are 2 or more races, yeah, here's, 40% are free or reduced, 60% are paid. For students who are Asian, 27% are free or reduced, and 73% are paid. So yes, this is it. Now I do just want those percentages. So I'm going to paste this in here. But then I want to do, this is a lot of editing. Speaking of editing, I should edit this out of the video or speed it up or something so you don't have to watch all of this. All right, there we go. A little tedious, but there we have the conditional relative frequency distribution of socioeconomic status by race or ethnicity. All right, so now we have a table that shows student gender and their seat locations in a large lecture course at a university. Suppose we choose a student at random. We want to find and interpret the probability of A given B. That's what that means, right? So we want to find the probability of A given B. That would be the probability that the student is female, given that she sits in the front row. So we're looking just at the front row. That would be 37 out of 52. 37 out of 52, which really is approximately equal to, not exactly equal to, 0.71. All right, now are events A and B independent? Here, let's set this new page. Are events A and B independent? All right, well, we need to know, is probability of A given B, is that equal to the probability of A? That's what we're wondering. So we need to find the probability of A, the probability that the student identifies as female overall. So female, 150 out of 236. And again, that's approximately equal to 0.64. So no, they are not independent because, oh, am I going to be able to do, let's do this. A given B, I can do my not equal to in here. Not equal to probability of A. I don't know how to do the regular character. All right, and that is it for this video. A little lengthy in here, but hopefully now you can understand all of these questions from exam 2, our second exam in Math 120.